Namaskar. So in this video we are going to start the new topic, that is block diagram reduction. Okay, so in previous lecture we were discussing about the mathematical modeling of control system. We have also dealt with FV and FI analogy, what is transfer function. In this lecture we are going to start the new topic, that is block diagram reduction technique. So what is block diagram model? So if a given system is complicated, then in that case it is very difficult to analyze it as a whole system. So from the transfer function approach, it is very easy to find the transfer function of each element of complicated system. Now by connecting these elements, complete system can be splitted into the different blocks and can be analyzed very easily. So block diagram is nothing but a pictorial representation of the given system, and it is the very simple way to representing the given complicated system. Now by arranging these blocks in a proper sequence, it is easy to show the interconnection of the system component to form a system. Now it is shows that the cause and the effective relation existing between the input and output of any system. So let us start what are the contents that we are going to discuss. So whenever we are converting any physical system into the block diagram representation, we have to deal with some kind of form, that it can be connected in a cascade form, it can be connected in a parallel form, might be feedback form, or we have to move some blocks to simplify the reduction technique, and we are going to solve some example on the basis of this different form. Okay, so that is what we have discussed about block diagram. It is nothing but subsystems are represented in a block diagram as a block, and each representing a transfer function. So this you can see, this transfer function is G1 of S. It is nothing but the output V2 of S divided by V1 of S. So each gain block is a separate transfer function. So this much of transfer function are connecting in a cascade and parallel and feedback and some another form. Okay. So in this unit we will consider how to combine this block corresponding to individual subsystems so that we can represent whole system as a single block. So ultimately we are going to convert this much of complicated system into a simple block, that is a single block. Here we can convert using the block diagram reduction rules, that is these all are the rules. Okay. Now here is one of the example of reduction. So here you can see this complicated system can be converted using the block diagram reduction technique in a single block. Here you can see the input of the system and output of the system, that is not going to vary because we are not converting, but we are finding the equivalent network by using reduction technique. So here you can see a simple block diagram of it can be seen that it is only one input is there and one output is there, and this is the block that represent any system. So it can be represent the behavior of such kind of system, and gain is given by G of S. So if you want to find the transfer function of this system, that can be written as G of S is equal to the output of the system, that is C of S, divided by input of the system, that is R of S. So G of S can be written as C of S by R of S, and from that we can write C of S is nothing but R of S multiplied by G of S, that is written here. So whenever there is a block and you want to find the value of transfer function, it will be output upon input, and when you will be interested to find the value of output, in that case it will be the transfer function multiplied by input. Here you can see the transfer function G of S multiplied by input. So output will always be a transfer function multiplied by whatever the input is. Okay. So here first let us summarize the different elements of the block diagram. R of S is nothing but the input signals, and C of S is nothing but the output signals. As far as system is concerned, the input and output is subjected to one particular system. In that case it is G of S, and the transfer function, that is G of S. If you want to find, it will be C of S, that is output divided by input R of S. Now we consider the form in when blocks are typically connected and how these forms can be reduced to a single block. So let us say this kind of system will be there when number of input signals are applied, and this is nothing but your summing point. Also this point is also known as your pick off point or take off point. Generally I am going to use as take off point, not pick off point. I am going to use take off point. It is also called pick off point. Okay, it doesn't matter. So here we can see that R1 is going inside the summing point, the sign is positive. R2 is going inside the block, sign is positive. R3 is also going inside the block and the sign is negative. So the total output, so these are the input signals. Okay, so value of output signal, that is C of S, will be the total of R1 plus R2 plus R3, but you can see that this signals having negative sign, that is why R1s plus R2s minus of R3s. Okay, this is very easy. So this is all the operation of summing point or summing junction. Same way, take off point is nothing but whatever the signals is coming inside that point will going to outside. So if we are dealing with a three direction, if we are departing one signal into three part, then it will be the value will be same. So whenever we are dealing with the closed loop control system, that is what happening now. This is the block diagram open loop system. In closed loop control system there will be summing point right here, and we are taking a backward signal from this point. So this, in this direction it is also C of S, in this direction also it will be C of S, and this error detector will going to find the deflection or the error into the controlled variable. Okay, so this is what the summing point and takeoff point is all about. Input signal, output signal, and what is the system. Now with that let us try to understand the different rules for block diagram reduction technique. The first rule is very simple, that is cascade form. Now what is cascade? We can sometimes call it is series connection. Okay, so when multiple subsystems are connected such that the output of one system serve as input to the next system. So you can see this is input to one system. Now this output of one system given to input of another system, output of this system given to input to another system, and ultimately we are getting output. Okay, so these subsystems are said to be in a cascade form. So when this kind of system will be there, let's say just ignore this G1s into RS, ignore this underline, whatever I am underlining, just ignore this. So input is R of S, output is X2 of S. Now if you want to find X2 of S, that is nothing but the transfer function multiplied by input. So here it is the transfer function G1 of S multiplied by input R1 of S. Same way, now the input will be X2 of S in this case. So if you want to find the output right here, that will be the transfer function, that is G2 of S multiplied by whatever the input is, that is G1s into RS. Same way, if you want to find output for that, transfer function multiplied by input. Here the input is G1 G2 into R. So your output total will be G3 into G2 into G1 into R of S. Okay, in short we can say the input signal R of S and output signal C of S can be represented whenever these three blocks are connected in cascade. We can represent it in a single block by multiplying the gain of all these blocks, that is G1, G2 and G3. So the reduction will be G1 multiplied by G2 multiplied by G3. So when three blocks are in a series or in a cascade form, we can just directly multiply the gain of the blocks and we can find the reduction. Okay, so this is the simplest form. You have to just multiply these three blocks. Here is the example how we are getting this term G3 into G2 into G1, but ultimately you don't have to explain this. You can directly convert into G1 into G2 into G3. So the algebraic form of the final output clearly shows that the equivalent system transfer function is the product of the cascade system transfer function. Okay, now just ignore for right now. Let us try to understand the second reduction rule, that is parallel form. So it means in first case all blocks are connected in series, Here all are connected in parallel. You can see G1, G2 and G3. Now for if you want to find output at this point, if you want to find output at this point, and if you want to find output at this point, all will be different. At this point it will be block, that means transfer function multiplied by input. The transfer function is G1, input is Rs, so it will be x1s output, that is equal to Rs into G1s. Same x2s is equal to the transfer function multiplied by input. Same transfer function G3s multiplied by input R1 of s. Okay, and then we are going to add this. In that case we can get G1s plus G2s plus G3s, respective sign will be there. Here it is plus, then it will get G1 plus G2 plus G3. If will be minus all three, then minus G1 plus minus G2 plus minus G3. So this is just the explanation. But whenever these one or two blocks are will be in parallel, you just have to add this and you will get the reduced block diagram, that is G1 plus G2 plus G3, or G1 minus G1 plus minus G2 plus minus G3 in case of negative sign. Okay, so the equivalent transfer function is the sum of parallel transfer function with matched sign at the summing junction. The sign is very important. Okay, you have to take care of this sign. If positive is there, in that case this sign will be positive. If negative is there, in that case it will be negative. Now the third is the feedback form, that will be also known as the closed loop function. Okay, these three rules are very important. The first, second and third, you will the 60% of time having this kind of situation where the series connection will be there, or the parallel connection is there, or the feedback will be there. Okay, so these three are very important. So here you can see this controller G2s and G3s are in series, so you can directly convert into single block by multiplying G2 into G3. Same way you can find H1 into H2, okay, because these are in series. So here G1 multiplied by G2 is nothing but G, that we have represented right here. Same H1 into H2 is nothing but H of s, that we have represented right here. This is your input signal, C of s is output. This is your summing point where actual value and your reference value are going to compare it, and it will generate an error signal, and that is going to fed again to controller, and it will try to correct whatever the error is. Okay, so simply we can say this is the block diagram of closed loop control system, and we want to find the transfer function of the system. Here Rs is input signal, Es is error signal, Gs is your forward path gain, H of s is feedback path gain, and C of s is output. Here also one signal, that is B of s, that is backward signal. Okay, now from this figure again we are showing the same figure. We can write E of s is nothing but R of s, E of s is nothing but R of s minus or plus. Now here the output will be the transfer function multiplied by the input of the signal. Here the input of the signal is, here the takeoff point is will be there, that is why C of s is going to this direction and also in this direction. That is why the input right here it is C of s. So the output at that point is nothing but transfer function H of s multiplied by the input, that is C of s. So you can write E of s is nothing but R of s minus or plus H of s into C of s. Okay, same way you can write the output at that point will be C of s, and it will be E of s multiplied by G of s. It means the transfer function multiplied by the input of the system, that is E of s. Okay, so these two equations are very easy. Now if you put the value of Es into this equation, here you can see Es, and if you put this equation right here and you take the ratio of output, that is C of s and R of s, okay, you will get C of s by R of s is equal to Gs divided by 1 plus or minus Gs into Hs. So let me just put the equation right for you, that is C of s is nothing but E of s, that is R. I am writing as term, so R minus or plus C into H, okay, and this is the whatever the value of E, and then G. Okay, now we can see that G of S and R of S is here and C of S is output. We want to find the ratio of output upon input. It means the C of S we need to take it this side. Okay, so if you take this term this side, in that case it will be C, let us consider that is minus only, not plus. In that case C plus C into H into G is equal to R into G, because R is multiplied with this. Okay, now you can take C outside. In that case it will be 1 plus H into G. Okay, this C is taken outside and that will be R into G. Now we have to take the ratio of C by R. So C is right here, just take R in the denominator, it will be C by R, and it will give you this G is right here. So G divided by 1 plus GH, 1 plus GH. Okay, that is what right here, G divided by 1 plus GH. Here we have considered minus sign, that is why the here sign is plus. If we have considered plus sign, in that case it will be minus. So that is why here you can see minus or plus, here it is plus or minus. Okay, so in that case of minus, it means if the feedback is negative feedback, in that case the sign will be positive. If the feedback is positive feedback system, in that case sign will be negative. Okay, so this equation you have to keep in mind, that whenever a feedback kind of control system is there, it means you can see there is a forward direction and another one is feedback direction. So there is a difference between a parallel and a feedback. You can see the summing point is there, but here the direction is forward, here the direction is backward. So you have to differentiate between the parallel and cascade feedback element. Okay, in that case you can simplify this whole block diagram into this one block, that is GS divided by 1 plus or minus GS into HS. This is the most important block diagram reduction rule. Okay, you have to use it many times, and in that case you have to remember that whenever this forward path is there, backward path is there, if negative feedback control system is there, in that case it will be positive, in positive it will be negative, G divided by 1 plus GS into HS. Okay, so you will get it in a short time, you don't have to worry about that. Now how we can move the blocks around. So let us take an example that a system block diagram may require some modification before the reduction discussed in above can be applied. So sometime we have to move the summing point and block around to find the easiest way to deal with your cascade, parallel and feedback form. So we may need to move blocks either to left or right of the summing junction. So in that case you can see that your input signal is right here, the another signal is adding at summing point, that is X of S, and your gain block is G of X, your output signal is C of X. Now in that case what we are interested to find, we want to move this summing point ahead of the gain block. Okay, this is what we want to do, and at that time you have to add one extra block that you can see that this summing point is now at this point. Okay, in that case you can see one extra gain is added with X of S, that is G of S. Now same thing but in opposite direction, you can see that your summing point is right here, that is before gain block. You can see this is the mirror image, and in that case you have to do your summing point needs to be ahead of the gain block. In that case you can see in place of G of S it is 1 divided by G of S. The same X of S is right here, you can see in all places. Okay, so this is what the block diagram reduction, whenever you are moving your summing point before gain block you have to add G of S, and whenever you are moving your summing point that is after gain block you have to add 1 divided by GS. Okay, now I am not going to prove this how we can come to this point, but this is very easily understandable. But you have to remember, okay, this is nothing but if you find the value of C of S, then it will be g of s multiplied by whatever the input. Okay, so input in this case it will be r of s plus or minus, here it is minus or plus, that is by r of s minus or plus x of s. Okay, now if you just check c of s in this diagram, the value will be same, but if you just first remove this gain block c of s and try to find the value of c of s, that will be different. Okay, so to match the value of c of s in both the cases, because we are finding the equivalent circuit only, we have to put one extra block, and that block is nothing but g of s. So mathematically, that whatever I said right now, that you can formulate mathematically. In that case you will understand that g of s that we have to add. If you have any doubt, you can ask me and I'll show you how to find it mathematically too. You will find in any books. Okay, same way if you doing opposite, if you are converting, you are moving this summing point before a gain block, in that case you have to add 1 divided by g of s. Okay, here g of s only, here 1 divided by g of s, same thing is there. Okay, in both the cases you can find the same way. Now if you understand the concept of moving summing point before and after, you can easily understand the concept of takeoff point. In case of, let's say, summing point, it is a takeoff point right there, it is x of s, input is there r of s. Okay, one gain block is there and output is there. If you want to just move this takeoff point ahead of the gain block, here it is g of s, but in case of takeoff point it will be 1 upon g of s. The same way, if here it is takeoff point, not the summing point. Okay, and if you want to move that before the gain block, in that case here it is 1 upon g of s, but in case of takeoff point it will be g of s only. Okay, so once you remembered the moving of your summing point before and after, you can easily remember with dealing with your takeoff point. It is the same thing. Okay, that we have explained right here, so we don't have to worry about this right now. So now from this much of rules, let me show you some of the example so you can easily understand what we are dealing with. So the example is that reduce the following system to a single transfer function. You can see the different block represent a transfer function, but with block diagram reduction technique we are interested to find a single block. Okay, a single transfer function. So here you can see these two blocks are in series, so you can easily find the transfer function or the reduction of these two, which will be g2 multiplied by g3. It will be g2 multiplied by g3 of s. Okay, I am not saying g3 of s, but it will be always there. Now you can see that this might be the forward direction, and same you can see this is the feedback direction or the backward direction, and this representation is nothing but your third rule, that is feedback form. Whenever there is a forward direction element is there, feedback will be there. In that case it will create a loop, and for that you have to remember the transfer function can be found out by, here you can see that the sign is negative, it means the negative feedback system. It means the transfer function can be written as g divided by 1 plus g into h. If the negative feedback system is there, the sign here will be positive. Okay, sign here will be positive. Now g is nothing but forward path gain, so forward path gain in this case is g2 into g3. So in place of g you have to put g2 into g3. Okay, same here, in place of h you have to put h1 of s. Okay, so it will be g2 into g3, same g2 into g3, and here it will be h1. This will be your transfer function of this much of part. So this much of part we have reduced into one block, and that block is this. Now again you can see this block will be in forward direction, again it is in one is in feedback direction, that will also create one loop. So same formula we can use, that is g divided by 1 plus gh, but here you can see the positive feedback controller system is there, that is why we have to use minus in place of plus. Okay, that will consider also one extra block. Again the feedback loop is there, third loop. If you apply third loop, that entire portion can be converted into a single block, and that can be in series or cascade with this block. And if you just multiply this, you will convert this following system in a single transfer function. So same thing is done right here. You can see this is one way. Now this is a good example of what I have to convey to you. Block diagram reduction technique is not we can say that any physical system can be represented in block diagram system by one way. You can simply find in any other way. Okay, so whatever I have explained in a previous slide, the concept that we are using in this reduction is different. Here you can see this, you can see that H1, H2 and H3 are in parallel. Okay, so first we are dealing with this part, and this will be easy for you. Whatever I am explaining to you was such a difficult, the same way you can find the same transfer function, okay, but the method will be different. So here you can see this 3 branch in parallel, so here the sign is minus, that is why H1 of S minus H2 of S, H3 of S. Here I have made one mistake, that is minus H1 plus H2 minus H3. Okay, this will your feedback element, because these are connected in parallel. So in parallel what we are doing, we are just adding these blocks. So this addition of this block will be H1, H2 and H3. Okay, so if I consider here sign is minus, that is why the whatever I have written was correct. Now if I am saying that it is minus, plus and minus, in that case the sign will be plus. Okay, so here same these are connected in cascade, so your single transfer function will be G2 into G3. So this is your forward path, this is your feedback path. You can easily find with G divided by 1 minus CH, because it is plus right here, so 1 minus CH. It will create one block, and this block will be in series with this G1. You can see G1 will be right here. That is why the multiplication was happening. So if you just look at this term, it is nothing but the solution of this feedback control system. Okay, and it will your transfer function, final transfer function. So you can represent entire block diagram into a single transfer function using this block diagram reduction rules. Let me take another example. Reduce the following more complicated block diagram. Here you can see the complexity is more. So rightmost feedback loop can be reduced. So first you can see when you look at the block diagram, it click the first thing that you can do. Here you can simply find that this block diagram is easily converted, because you can see this forward path and feedback path is there. You can easily use G divided by 1 plus GH and find the transfer function. Okay, now you can create the parallel form by moving G2 left side. So you can see G2 right here. If you move G2 in this direction, or you can see if you are moving this takeoff point in a forward direction, and you have to remember the rule, whenever you are putting your takeoff point, shifting your takeoff point ahead of the gain block, you have to add 1 divided by whatever the gain block is. That is why 1 divided by G2 of S. Now it will be come after the practice that what rule you have to use at which time, because if you look at the block diagram after some amount of practice, you will be tell that this reduction rule should be applied. Okay, so here you can see this branch has gain 1 right here. No block diagram means it has gain 1. But now after doing this transformation, having the gain 1 divided by G2. Okay, so this is the same figure that previously we have discussed. Now reduce the parallel form involving the 1 divided by G2 and unity. Here you can see this point and this point now the same only. The direction of this is forward direction of this gain is also the forward direction. It means this branch and this branch are connected in parallel. In parallel the sign is also positive, so you just have to add both this gain. It means gain of this is 1, gain of this block is 1 divided by G2. So here it is 1 divided by G2S plus 1. Once the summing has already done, we don't have to worry about summing point, so you can just eliminate that summing point. Okay, Now push this G1 to the right past the summing junction to create a parallel form in the feedback path. Okay, so if you just look at this, you can clearly find that if you move this summing point ahead of this gain block, okay, you can see G1 and G2 will be in series. Okay, that is what we have done, G1 multiply by G2. And first you have to remember, whenever you are putting or shifting your summing point before gain block, you have to add whatever the reciprocal of whatever gain block is there. So H2S is already there, but we have to add 1 divided by G1, that is H2S divided by G1S, you can see right here. Okay, we have shifted this gain block right here, and G1 and G2 are in series, that is why G1 into G2. Now same again I am showing right here, reduce the parallel form. Okay, so parallel form is very easy. This summing point is also there, this is also summing point. This is in feedback path, this is also feedback path, so both are connected in parallel. Then if we want to consider the same sign negative, then in that case this is positive, H2 of S by G1 of S plus H1 of S. So we are just adding both these because they are connected in parallel form. Okay, now here you can recognize that before that you can see this, both the blocks are in series, so just add using cascade form. In that case you can see that this is now the feedback form. Feedback element means the forward direction, the feedback direction, the negative feedback control system, so it will be G divided by 1 plus GH. Now put the value of G is equal to G1 into G3 and H is equal to whatever right here in this block. If you put inside this equation, you will get this much of big transfer function. Now you can see this transfer function and this transfer function again connected in cascade form. By multiplying both this equation, you will get the final transfer function of your this particular block diagram. So you can convert this much of complex system into a single block diagram. In that way you can analyze the behavior of the system. Okay, both the things is same, only we are dealing with a reduced block diagram. Okay, so with this we are closing our today's lecture. You can do as many of as example. We have already discussed many of the example. Some of the example you find very easy, some will be some complex. Now there are also two reduction rules that are very important, but the amount of time that is going to ask in examination is very less.